All right, so let's go ahead and work an example problem using superposition. I'm going to pretty much use the same circuit. I got a couple of different slides here that I'll use, basically just so that I can solve each sub-circuit on a different slide. Let's go ahead and make this a current source and then a resistor here. Okay, is this the same circuit I was working with? Yeah. All right, good. So let's go ahead and give this a ground. Probably have to split this up into two videos. So we'll do one where I solve the first circuit where there's no voltage source, and then the second video where I solve the second one. Let's go ahead and call this a 10-volt source. We'll make this a 2 milliamp current source, and then we'll just go 1K. Let's go 8K and then 2K. How about that? And what we're going to be interested in finding in this circuit is Vx, Vy, and Vz. All right. And so if we remember from the previous video, there's basically going to be two sub-circuits that we need to solve. There's going to be one where we short the voltage source and we solve the rest of the circuit with the current source included. All right. And then there's going to be one where we need to keep the voltage source, but we open the current source and we solve the rest of the circuit. Okay. And so in these two circuits, I'm basically going to call this will be Vx1, Vy1, and Vz1. And then this will be Vx2, Vy2, and Vz2. All right, we're going to learn a lot from this example. I think there's a lot of good principles in this problem. But let me go ahead and take this main circuit and copy it over into the other slides so that I can work on it. Okay. So here we'll have the one with the source, the voltage source shorted. So I'll go ahead and draw that. Oops. So there's my short. And then in this case, I'm going to solve for Vx1, Vy1, and Vz1. And then in the second case, I'm going to have the same circuit, but with the current source removed. Okay, and that's an open. And then I'm going to call this Vx2, Vy2, and Vz2. And I'm going to solve for all those values and then sum them up at the end. And let me just write that here, that Vx is equal to Vx1 plus Vx2. Vy is equal to Vy1 plus Vy2. And Vz is equal to Vz1 plus Vz2. All right, and that's going to give us our final answers right there whenever we get there, okay? But for now, okay, so we split our circuit up into the two separate circuits that we need to solve. And the first one is going to be this one. And so the first thing that we can recognize, and maybe you don't recognize it but right away, but you'll learn to recognize stuff like this, is that the 1K resistor and the 8K resistor are actually connected in parallel, okay? They do share two nodes. They share this node and they share this node, right? And so they're connected in parallel, so I could redraw the circuit as this being my equivalent resistor, and then I've got a 2 milliamp current source, and I've got a 2K resistor there. I need to figure out what that REQ value is. It's going to be the two resistors in parallel. Well, REQ is going to be 1K times 8K over 1K plus 8K, because that's my formula for two resistors in parallel. So let's go 1 times 8 divided by 9 gives me 889 ohms roughly, or 8.888889K. So let's just say 889 ohms. All right, and now my goal here was to solve for Vx1, Vy1, and Vz1, right? Well, Vx1 right off the bat, I can see is 0 volts, right? It's connected to ground. So let's just write that right away, that this is 0 volts. Okay, so Vx1 is 0. And from this other circuit that I just created here, I've got Vy1 here and Vz1 here. And I need to solve for those, okay? Well, pretty easily I can find both of these because I have a 2 milliamp current source and I can use Ohm's law, all right? So I know that Ohm's law, well, first of all, I know that, let me go ahead and move REQ outside so I can do this. I know that the same current flows in this entire loop, right? So basically I have 2 milliamps flowing through the 2K resistor. I have 2 milliamps flowing through the 889 ohm resistor that we found as the equivalent. Let me go ahead and label my plus to minus for these currents because of the way that the current flows, and let's go ahead and solve for them. So Vz1 is pretty easy. Vz1 minus 0 is the drop across this 2K, right? I have 0 volts here because it's ground. And then that's going to be equal to I times R, which is just going to be 2 milliamps times 2K, which basically tells me that Vz1 is equal to 4 volts, okay? So I got Vz1, I've got Vx1. The last thing I need to do for this sub-circuit is I need to find Vy1, which again I can do pretty easily. I can look at this resistor here, and I can say that basically my 0 volts is on the plus side, minus my Vy1, which is on the minus side, is equal to I times R, which is 2 milliamps times 889 ohms, or 0.888K. So I need to basically multiply that by 2. I get that negative Vy is 1 is equal to 1.778 volts, or I can write that Vy1 alternatively. I can multiply both, I can multiply both sides by -1, and I can obtain that Vy1 is negative 1.778 volts, okay? Go ahead and put a box around that. And so we have determined Vz1, Vy1, and Vx1, and we are done with this portion of the superposition problem. Remember, there's two equivalent circuits. There's the one with no voltage source, and there's the one with no current source. We just found all the values for this one. We found Vx1, Vy1, and Vz1. In the next video, I'm going to solve for Vx2, Vy2, and Vz2. And then we will sum the results up, and we will get our final answer here for Vx, Vy, and Vz. Okay? So we're just going to go ahead and end the video right there.